Now, strong nucleophiles, strong nucleophiles, primary substrate, primary substrate, and sufficiently good leaving groups, good leaving groups, then polar aprotic solvents, polar aprotic solvents. These are the factors which is affecting the reaction of SN2 reactions. Okay, you require strong nucleophile for SN2 to occur. You require strong nucleophile. You require primary substrate, and the substrate should have a good leaving group, and the solvent should be polar aprotic solvents. Generally, it will be faster in polar aprotic solvents. So these are the general trends in the nucleophilicity SN2 reaction. Now come to the strong nucleophilicity of different groups. When you talk strong nucleophile, see, suppose you have nucleophiles like this, CH3 minus. It's a good nucleophile, CH3 minus. Then NH2 minus, OH minus, or OCH3 minus, OH minus, then F minus. All these are strong nucleophiles, but their strength is different. This is the most strong nucleophile. It's very, very strong nucleophile, CH3 minus. Then NH2 minus is still stronger, is slightly weaker. So the strength of nucleophilicity is in this order. Okay, this is the order of strength of nucleophilicity. That means CH3 minus will react in SN2 reaction faster than NH2 minus, faster than OCH3 minus, OH minus. Okay, so this is the order of and the primary substrate, secondary substrate, tertiary substrate, you know, primary carbon what it is, secondary carbon, tertiary carbon. Primary compounds only will react under SN2 reaction. Okay, then comes secondary, tertiary does not react. Now let us look at SN1 reaction. SN1 reaction. Substitution nucleophilic union molecular. Now let us look at the kinetics of this reaction. If you measure if you do kinetic experiments, that is date determining experiments. Just one second, some disturbance. Okay. So if you do the kinetic experiments using with this type of reaction, the kinetics of the reaction rate is proportional to rate of reaction is equal to a constant into concentration of substrate, and it is independent of concentration of nucleophile. Rate of reaction is independent of concentration of nucleophile. What's it? Of concentration of nucleophile. So it is independent of concentration of nucleophile. Then what happened? Who has come? Okay, somebody has come and then gone. All right. So independent of concentration of nucleophile. of nucleophile. Then so independent of concentration of nucleophile, and then that means if you change the the concentration of nucleophile, the reaction rate will not be affected. That's the meaning of this. What is meant by independent of concentration? That is, you do two experiments. Say, for example, you do a reaction at a concentration A, at a concentration of A of nucleophile, and at a concentration of B of nucleophile, double. You take double of this to A. Okay, you have changed the concentration of the nucleophile and then did this experiment. You can see that reaction rate is same reaction rate, same rate. That means if you change the concentration of nucleophile, the rate of reaction does not change. Such reactions, such substitution reactions, you can categorize as SN1 reaction. Okay. Second, now the SN1 reaction. An example we can take. Look at this one. It's a tertiary alkyl halide. You react this with water. Simple. Water is a nucleophile. It's also acting as a solvent for the reaction. Okay. Such reactions in which water, the solvent is acting as a nucleophile. So this is nucleophile and solvent. Such reactions are called solvolysis. So what is solvolysis? A substitution reaction in which the solvent is acting as a nucleophile. Okay, and what is the product here? You get tertiary butyl alcohol plus HCl. Tertiary butyl alcohol plus HCl. Okay, so you can see you are using excess amount of tertiary butyl water and excess amount of water will also, therefore you are not concerned about the concentration of the water. Okay, now so this is now let us look at the mechanism of this reaction. The proposed mechanism involved two steps. The proposed mechanism involved two steps. Step number 1, formation of carbocation. Formation of carbocation. Formation of carbocation. Now what is the formation of carbocation? See what carbocation will be formed. Look here. I have Cl. It gives you plus. Okay. So I will draw it in a three-dimensional fashion like this. So this also should be three-dimensional. Okay. So I will put the arrow in this way, plus Cl minus. Now what? Now see here, look at the first step. It does not contain anything. And now in the second step, look at the mechanism. H2O. Water molecule comes and attacks this. From any side, you will get OH. Okay. Or you can draw this in this way, in a planar form. That also is correct. See here. If you simply draw this, you can draw like this also. You have positive charge plus Cl minus. Okay. Now this can give you this product. Or it can, the OH can be coming from the opposite side. Both are possible. That's okay. That we'll see that. Now let us look at the geometry of this. See here. What is it now? When you measure the kinetics of the reaction, this is step number 1. This is step number 2. Step number 1 is a slow step. Step number 1 is a slow step. Step number 2 is fast. How do you know this? How do you know this? Look at the stability of the starting of the product in each case. Look at this one. This is neutral molecule. Neutral molecule. This is a carbocation. Okay, remember carbocation is higher in energy. Higher energy. Neutral molecule, lower energy, more stable. And so, you are going from a low energy to a higher energy state. Will it be fast or slow? It will be slow. Quite naturally, it will be slow. And therefore, this is the first step is, okay, come so late. So the first step of the reaction is a rate determining stage. The first step is a rate determining stage, and then first step is the rate determining stage. In the second step, you can see this high energy state is attacked by a nucleophile, and you get the final product. So that is a fast step because high energy to a very low energy state. So if you draw an energy profile diagram of this, see here is your starting material. It goes up, it comes to an intermediate, and then it goes far down. This is the case with an exothermic reaction. So this is the energy of the starting material. And this is the energy of the final product. So this is the overall delta H. Delta H. Now look at the first step. This is the transition state, first transition state. Remember, this is not the energy of the intermediate. It is a transition state in which you have only this one. See here, This is the transition state. The CL is not completely broken. And here, this is the energy of the starting material. Now here, this is the intermediate energy. What is the intermediate? Carbocation is the intermediate. Okay. And now here, this is transition state 2. So what is that? It is this one. So nucleophile is coming and attacking. And that is this transition state. That is this transition state. So transition state number 1 and transition state number 2, TS2. And what about this one? This is intermediate carbocation. Intermediate carbocation. So, and the overall energy of the reaction is delta H. And this is the first activation energy. And this is the second activation energy. So this is the energy profile diagram of a SN2 reaction. ഇതെല്ലാം സമയം എഴുതി വെക്കേണ്ടിരുന്നു കണക്ഷൻ കിട്ടാത്തതാണോ പ്രശ്നം എന്നോ എനിക്കോ ഞാൻ ജസ്റ്റ് ഒരു സമയം എഴുതി വെക്കാം ഞാൻ 9:14. Okay, now, Gilna. All right. Okay, so this is the now let us look at the stereochemistry of this. So that is energy profile diagram. This is the energy profile diagram or energy diagram. Energy diagram. If people come in between and have a disturbance, that is a real problem. Okay, now, so this is the energy profile diagram of this reaction. And let us look at the stereochemistry of this reaction. Stereochemistry. If you now you can guess the stereochemistry of this reaction from the mechanism. From the mechanism, you can see what product is formed. Suppose you are taking this starting material. See here. Suppose this is your starting material, R1, R2, and R3. You will get intermediate R1, R2, R3 with a Rachima. Okay. So, if this is yeah, this is the carbocation intermediate, and you have the empty orbital perpendicular. Suppose I rotate this along this axis. I rotate this 90 degree along this axis. I'll have the R1 here. This R3 will come closer to me. R3 will be projecting towards me. And R2 will be exactly behind. And then we have the empty p orbital here. Empty p orbital. Now, once you have this empty p orbital, then what happens? So this is your first step. So I'll put an OR here. See, rotation by 90 degree. Rotation by 90 degree. Now in this step, the nucleophile can attack. Now see here, we have the nucleophile here, OH2. The nucleophile can attack either from this side or it can attack from this side. Both are possible. Both are equally possible. Both are equally possible. Okay. And so, what are the possible products? You will get two products in which one OH is on this side plus a product in which OH is on the opposite side. Oh, sorry. Plus the mirror image of this. In the case of these two, this starting material, these two are same. Since there is no difference between R1, R2, R3. So I can say, I should have drawn like this. I will draw R1 here. Oh, I will draw R1 here. One second. So R1, R2 is closer to you, and R3 is behind. And you can have the opposite product also. What is the opposite product? What is the opposite product? Hands are paining. What is the opposite product? This is the opposite product. Mirror image of this. R1. Oh, my hands are paining a lot. R3 and R2. Okay, and OH is on the opposite side. So look here, these are mirror images of each other. So you have equal probability of getting these two products. If one is R, this is a non-superimposable mirror image of this will be S. If this is R, this has to be S. I don't know whether it is R or not. Because, okay, we can specify this only if we have what is R1, R2, R3. Okay. Anyway, you will get equal mixture, equal amount. Equal amount. And so what is the consequence? The consequence is, if you start with an optically active starting material, you will have a product which will be optically inactive. Okay, so the chiral carbon is affected. See here, the bond with chiral carbon is affected, and the bond between chiral carbon and chlorine is broken. It becomes flat. See, this is flat. When it becomes flat, it can be attacked from either side, and therefore you get a mixture of two different products. Okay, so a mixture of, so that means the stereochemistry of SN1 reaction is racemization. Stereochemistry of SN1 reaction is racemization. Okay, so these are the different aspects of SN1 reaction. Next time we will take up what is the effect, of substrate, nucleophile, leaving group, and solvents on the rate of even reactions. SN1 reaction. After that, we have to take up equally competitive reactions, which are elimination reactions, where you have even and E2 mechanisms. Okay, so we will have a class tomorrow also. Even though it is Saturday, we will keep 6 days, 8:45 to 9:30, and I will suggest please come in time. I know there may be connections, but connections, if you try, you will get. Okay, it is okay. But I think I am getting connection almost every day, somewhere around 9:30. Almost many days I am getting connection. There may be delay, but don't tell me that we are not getting connection at all. Okay, in your area, suppose you are telling me, I will believe it. I have no option. But if you are getting connection, then I don't think. So try as much as possible to reach in time. And I see, even if you may be genuine. I'm not accusing you, please. So I will prefer you people to come in time, so that you will get the benefit of it. Or at least you can, I'm uploading these in as videos. I will appreciate if you can observe the video. Okay, so at least do that.